and then infiltrate it into the subgrade, or hold it in the pavement and then let it run out at a much slower rate later. This has been proposed and is being used in pilot projects in various states as an alternative stormwater best management practice. Shoulder retrofit in low-speed areas, potentially for mainline pavement for some local road use. These need to be designed for hydraulic and structural performance. There's a design manual from NAPA that's available, and there is a design method that's been developed for heavy vehicles, developed for Caltrans, not yet validated, but there's work going on to be able to carry heavier vehicles on this type of pavement. In terms of long life, just as an example of a type of strategy that can be evaluated, long life asphalt rehabilitation has been used by a number of states, particularly for high traffic volume places where you want to get in and get out and then stay out for a long period of time. This can be used for rehabilitating existing concrete pavement or existing asphalt pavement with cement-treated bases or granular bases. You can go in and do an asphalt overlay, which can involve crack and seat or rubbleize the concrete and then place a thick asphalt layer with each of the materials in the different parts of the asphalt overlay optimized for a different purpose. Or you can remove, to maintain existing grade, you can go in and remove part of that existing pavement and then replace with a full depth asphalt structure, which uses the same design concept as perpetual pavement. What you're trying to do in these cases is design the right material in the right place in the structure, get the right properties for the function, try and minimize the thickness of this while achieving that long life. The thinner we make it, the faster the construction can go. We can use performance-related tests to specify those materials' properties. And overall, what we're trying to do is to design the pavement to drive the distresses to the surface so that we can handle them through fast and relatively low-cost maintenance and preservation treatments and have the underlying layers last for decades and decades below that surface. So we're typically looking at a 40-year structural design life on the order of 40 years, high reliability, and then maybe 15 to 20 years replacement of a sacrificial surface layer. An example of a full depth structure is that sacrificial surface layer, which might be an open graded mix for safety and noise and smoothness. A top layer designed for rutting and cracking, 2 to 4 inches thick. A middle layer, which can have very high ramp content in it to provide resistance to bending and some resistance to cracking and rutting. And an example would be a rich bottom layer or some other layer that has high cracking resistance. And this is placed on what's left of the existing pavement that you've left in there. This is an example. There's a number of ways to go about this, and there is guidance from NAPA on perpetual pavement design. An example of optimizing those materials, which can result in a reduced pavement thickness and which improves our construction speed and also reduces our environmental impact. On the left-hand side, we have a pavement designed with the same standard material throughout the entire structure, and to get a 40-year design, 30-year design life in this case, we needed about 21 inches of pavement. Whereas if we can optimize each of those layers for a specific purpose and use the ME design, we can reduce that thickness and get the same 30-year design life with about 12 inches of pavement. Another thing we want to do, looking at sustainable pavement, improving sustainability, is to increase the use of local materials and low-impact transportation, which we've talked about quite a bit so far. One way to go about that, to set a high goal, would be to look at something like a zero-waste approach that includes recycling, a policy of recycling all pavement materials either on-site or at nearby plants. We need to do this without compromising the longevity, but it can be done with the technology that we have in terms of materials and structural design. Accelerated construction. We can, and this will be talked about in the next part of the presentation in more detail, but we can reduce the cost and environmental impact by accelerating the construction. We reduce the amount of mobilization and demobilization, less worker travel, and overall we produce, there is some short intense pain for the traveling public, but it minimizes the prolonged agony of standard construction and those orange barrels and cones out there and K-rails for long periods of time. We have techniques to accelerate construction, including designs and specifications to minimize thickness and speed construction, various traffic closure strategies. A lot of work's been done in the last 10, 15 years on traffic management planning, traffic monitoring, and being able to make real-time adjustments during the construction process. Huge public outreach and provision of alternative transportation can really facilitate accelerated construction. This is an example from a project. There's often a lot of fear at looking at things like 55-hour weekend closures or continuous closures. But the experience so far in many places has been, although there's a public perception that they don't want rapid rehabilitation or accelerated construction before construction, once the folks in an existing area have gone through it and realized it's not that bad and it's over, and then you have good pavement for a long time, the public perception can change substantially. So some dealing with that risk averseness at the beginning can produce some massive rewards by going to accelerated construction. Another consideration to reduce environmental impact is if we have multi-lane facilities, but only the outside truck lane is badly damaged, and this is my best attempt at drawing a cracked lane and uncracked lanes. If the truck lane is damaged and the inner lanes are not, one of the things that we can consider is rather than overlay the entire direction of travel or the entire structure, consider doing a partial reconstruction or a mill and fill of the outer lane and then doing a relatively thin preservation treatment over the top that gives that smoothness and restored riding quality and noise across all of the layers, rather than do the same structural overlay across all of the different lanes. We need to consider the use phase. This includes consideration of the traffic levels. The more traffic that's using the road, the pavement, the more we need to consider smoothness and fuel efficiency. We need to also consider noise and pollution associated with traffic and ways that we can deal with that with the pavement. We need to look at stormwater and consider urban issues of flooding and stormwater treatment, as well as hydroplaning and skid resistance. Other things to consider for each project context include aesthetics, potentially consider urban heat island, lighting, utility cuts. If we design a long light pavement and build it and it's cut up for utility cuts within a few years, we have not achieved our objective. So to summarize the design considerations, overall we want to achieve longer life or thinner pavement for the same life by integrating structural design, material selection and design, and construction quality, the right material in the right place, and trying to optimize and improve our ability to get construction quality through having an achievable pavement design. We want to maximize the use of recycled and locally available materials. We often have a lot of specifications out there that we've grandfathered in and nobody's necessarily looked at for a long time, particularly at the local government level, or if our consultants are basically grandfathering the same specifications forward into each project. It's worth taking a look back and see if we can adjust those to improve the use of recycled and local available materials without giving up much, if anything, for performance. We need to consider the use phase impacts, and we need to consider the longer life. What are we going to do at the end of this life? What's our preservation? What's our rehabilitation? And how can we maximize the same considerations, recycling, construction quality when we do that? Again, sustainable pavement design, look at the context. Use the best design methodology, consider the life cycle, and really take a look back. All practices can be reviewed and look at how we're doing things within an organization and to improve the sustainability using the basic approaches that have been discussed in this presentation. And this is a cartoon, and it's pretty funny, but I can't tell you the number of times that I've actually seen that exact quote put forward before when considering change. Some expected future directions. We expect our ME design capabilities to continue to improve. We should be taking advantage of them. Performance-related construction specifications, really making sure that we're getting what we want out of the materials. All these potential changes in new materials, particularly more recycled materials and potentially new binders. Integration of consideration of both cost and the environment into our design criteria, and more consideration in the initial design of what are we going to do in the future for preservation, rehabilitation, and recycling. And we'll pass it off to now look at construction considerations.
Very good. Thanks, John. We appreciate that background on materials and design. And we are going to turn it now over to Ahmad Al-Qadi, who will be discussing construction considerations. And quickly, before Ahmad starts, I would like to remind the audience that if they have any questions, please, we would encourage you to submit the questions using the chat box as we had indicated earlier, so that we'll be able to address those at the end of the session. So, Ahmad?
Thanks, Gert. Good afternoon, everyone. Just make sure here. Okay. You heard from Tom and John a little bit about how we can have our use of the materials and pavement design more sustainable. At this time, I will be discussing how we're going to be implementing this selection of the materials and design to make the construction practice more sustainable, while at the same time provide a durable and long life pavements. The construction activities, as you all know, it's including coaling materials and the subgrade preparation and base and subsurface layer placement and compaction. And if you look at this picture here, you can see the process of producing or constructing pavements. Every year there is around 500 million tons of new asphalt pavements that they are produced in the US, and they are coming from approximately 4,000 asphalt mixing plants. In the construction process, there is an excavation or maybe bringing some materials to the site and preparing the subgrade and make sure that we are achieving the CPR or the required CPR, and prepare the platform for placing the aggregate if it's a bound or unbound aggregate materials. And then compact these materials and use a prime coat. The prime coat is used in order to bond the aggregate layer to the asphalt layer. And after that, placing the asphalt layers, and if there is more than one asphalt layer is placed, we use a tack coat and up to at an optimized application rate. And of course, one of the most important tasks during the construction is the asphalt pavement compaction. Make sure that we are getting the optimized number of passes to get the desired density, which will affect the performance of the asphalt concrete tremendously, as you're going to be seeing here in a minute. There is 4 key issues related construction and sustainability. The first one is the fuel consumption, resulting from various construction activities, the exhaust emission influencing local air quality and global environmental impact, and the indirect effects such as that traffic delay, congestion, and noise emissions. And the 4th one is the pavement performance and the overall life, which affected by the construction quality, and the pavement material design. And we're going to be taking these 4 points here one at a time. The most important thing regarding the construction, that it is related to the energy consumption, and it's going to be affecting the surrounding areas, and it should be having an impact on the economy, which we should be considering as we are doing the construction process. So the first point we'll be discussing is the energy consumption and the greenhouse gases emissions. Pavement, as you know, during the construction, it is very energy intensive process, and the operation of the various type of equipment that we're using will be using direct energy, and of course the output of this will be some emissions that it's going into the air. So these are, or this process here, or the construction process, is an energy intensive process. The common energy sources that we are using for the construction are gasoline, diesel, propane, as well as the purchased and generated electricity. Of course, please note here that if the electricity is generated from coal, the emission is going to be significant, and if it's generated from nuclear plant, the emissions will be much, much less. In order to be able to quantify or to have an indication about the emission that we have in the air, we relate this into the economic value. So one of the terms that has been used by the EPA is the emission intensity. Emission intensity actually is coming from 2 ratios. The first ratio is the ratio of the emission to the energy. The emission is the outcome when we are putting the energy during the construction. And the second ratio is the energy related to maybe the population, maybe the economic value, whatever we choose to. In this particular case here, we choose to use some kind of economic unit, which is the GDP. So the emission intensity, if we use these 2 ratios, the energy will be canceled from both, and we will end up with an emission divided by the GDP. So in this case here, we are looking into comparing different sectors, or the emission from different sectors, while at the same time considering the economic output for these sectors. So the EPA used this to characterize the environmental performance for various industrial sectors, including the construction one. So if you look at this figure here, this is including various industry sectors. The first one is the oil and gas, and you can see the green bar here indicates the emission, which shows that the emission produced from this industry is very, very significant. If we look at the intensity, which in this case here, the emission divided by the GDP, you can see here that it is also a little high. The lower number is the better. If you look at the lime, for example, the intensity emission is very, very high, while the emission is relatively very low compared to the other sectors. The one that we are interested in is the one in the red box, which is the construction, and that's involved the various type of construction. We can see here the emission is kind of like, would say, in the middle almost, while the emission intensity is considered low. If we take this and try to compare it to the various type of construction here and focus on the emission intensity coming from the highway and road and bridge construction, we can find here that it is the highest. So the figure that you are looking at right now is dividing the construction sector into 3 parts. The first part, which is the yellow bars, it shows the construction of buildings such as the residential buildings. The second part, which is the green one, it's involving the heavy and civil engineering constructions such as road, highways, and bridges. And the blue bars are the ones related to specialty contractors, such as putting roofing shingles, or using drywall, and so on. So if you look at all this here, we can find that the one that it's related to the highway, road, and bridges has the highest emission intensity. And it depends here. If you look at the one, which maybe you want to trust my word on it, the one for the drywall contractors or construction, you can see that it has the lowest emission intensity. To put this in a little perspective, I can maybe give an example from the oil industry. If you are looking into the crude oil and you get from that the gas